So just to recap, you need to write this down because you already got it. Last time we ended up starting to look at plane autonomous systems, and so it's plane because it's two independent variables, x and y. Autonomous because there's no explicit t dependence on the right hand side. And then we talked about critical points, and critical points satisfy the condition that dx by dt is 0 and dy by dt is 0. And then we talked about stability, and roughly speaking what stability meant was that if we perturb slightly from the critical point, do we stay close to it or do we go away from it? It's basically what that definition we wrote down meant. Okay, so what we will do today then to begin with is let's see how we go about doing the linear stability. So let P, which is AB, be a critical point. And the equation, the number was 2.1. If you remember that equation, like that, we'd call that 2.1, I think. Okay, so that means that x of AB equals 0 equals y of AB. Okay, so don't get confused, because remember when we were doing the system with one equation, we had y of A equals B. Okay, these are different A's and B's. They're not connected with that. 2.3. So what we do is, well, what we're wanting to find out is if we perturb from that steady state, because stability is saying that if you move away from the steady state to begin with, you sort of push a little bit away, do you come back or do you shoot away? So what we want to do is figure out if we make a perturbation, what equation does that perturbation satisfy? So what we do, we set x of t to be a plus some xi of t, and y of t to be b plus some eta of t, where xi and eta are small. Okay, so then what's our first equation going to be? Dx by dt, well, a is a constant, so that's going to be dxi by dt equals x of a plus xi of t, comma b plus eta of t. And what I'm going to do then, obviously, is expand that by Taylor, x of AB plus, and I'll use this notation for derivative, partial derivative. That's at the point P multiplied by xi plus eta xy x eta at P plus high order terms. Okay? And a comma b is a critical point, so that's 0. And we do the same for dy. Dxi, well, dy by dt is just d eta by dt. And we do the same thing. Okay? And so now what we can do is we can write this in a form like this. The d by dt of z is equal to m times z, where z is xi eta, and I've been a bit lazy here by not putting in the function of t, but we know that there's a t is there, and the m is x differentiate it with respect to x. Sorry, I've made a mistake here. Of course, this should be x and y. Sorry about that. Because we're differentiating this with respect to this variable, and that's the variable x. So this should be x, and then we're differentiating this with respect to the variable y. So that'll be y, okay? Then you multiply by the xi and the eta. So that'll be xx, p, xy, p evaluated at p. So let's make sure we've got that correct, given that I've already made a mistake. So what would the first line be? It would, the first one would be dxi by dt equals m times z. So think about z. There'd be xi up here. So xi times this, which looks similar to that. Eta times that, which is that. Okay? So that's looking that it could be correct. And then this one will be yx at p and y, partial derivative y at p. Okay? And then we could just write that as a, b, c, d if we wanted to. Okay? And sometimes this m is called the Jacobian matrix. So what we've done is we've taken this non-linear system, 2.1, and we've reduced it to linear system, 2.5. Okay? And so the solution, well, it's a linear system, so the solution to 2.5 is just going to be z equals some z naught e to the lambda t. If we try that, then we're going to get lambda z naught e to the lambda t, we differentiate with respect to t, equals m z naught e to the lambda t. So you can see this is just like doing it if it was just one variable. So these cancel. And so we've got m minus lambda I, z0 equals 0, where I is the unit vector, is the unit matrix. So in other words, i.e. z0 is an eigenvector of m with eigenvalue lambda. Okay? And so therefore, if lambda 1 does not equal lambda 2, so so we should say that this is a second order matrix, so obviously there'll be two eigenvalues and two eigenvectors. So, so if the eigenvectors are different to each other, then the solution then z will be some constant z1 e to lambda 1t plus some constant z2 e to the lambda 2t, where c1, c2 are constants. So how did we get that? Well, we've got two solutions. If so we should just say that z1 is the eigenvector for eigenvalue lambda 1, and the same for Z2. So since this is a linear system, if we have solution Z1 e to the lambda 1t, then any multiplication by a constant will also be a solution. Likewise for this, and because it's linear, any linear combination is a solution. Okay? And then you should know that if lambda 1 is not equal to lambda 2, then Z1 and Z2 are independent of each other, so this is the full solution. So they're like a basis for R2, and this is the solution. So now you can see if these lambdas were positive or had positive real part, then Z would grow, which means xi eta would grow, which means we move away from AB, so AB is unstable. So the only way AB could be stable would be if both of these are either negative or have real part negative. Even if only one of them is positive, then you blow away. Okay? But that's in the case lambda 1 not equal to lambda 2. What about the case where lambda 1 is equal to lambda 2? Then we need to use, well, then the first thing is, obviously the lambda has to be real. First thing is that the lambda must be real then. Because if they were complex, then they're complex conjugates of each other. And so they wouldn't be equal to each other. Okay, so then this is a bit of recap from algebra course, Cayley-Hamilton theorem, which you've done in the previous course. That implies that actually m minus lambda I squared is 0. So therefore, there are two possible cases. Either m minus lambda 1 is equivalent to 0, or, actually that should be, no, that's a matrix, so we'll just keep it like that, or m minus lambda I is not equal to 0, but m minus lambda I all squared is equal to 0. So let's look at case 1. M minus lambda I is equal to 0. Then that implies m is just a multiplication of the unit vector, and so that implies that z equals some c e to the lambda t for any constant vector c. Okay? Because if this is the unit matrix, then you don't need to worry about it having to be an eigenvector, because any multiply I by any constant and you get the constant vector back. Okay? So any C is a solution. Okay? Second case would be where m minus lambda I is not equal to 0. That implies there must be a z1, there must be at least one vector such that z0 defined as m minus lambda I, z1 is not equal to 0. okay? Because if we couldn't find such a z0, then that would mean m minus lambda I was equivalent to 0, and that contradicts here, okay? Therefore, we can write the solution is C1 Z1 plus C0 plus C1 T Z0 e to the lambda t. Okay, so let's just check that. Check. So what's dz by dt? It's differentiate the exponential. You'll get lambda c1 z1 plus c0 plus c1 t z0 times e to the lambda t plus, because it's just a product, and then the next one will be differentiate this with respect to t, and we'll just get c1 z0 e to the lambda t. And now for this to be a solution, hopefully this will be the same as mz, okay? Because we're trying to solve dz by dt equals mz. So mz is lambda, let's see, sorry, I'm looking at that, I should be looking at this. So mz is c1 mz1 plus c0 plus c1t mz0 e to the lambda t. Okay, and because here I just took the m through, okay, so this looks promising because remember I'm trying to show that this is the same as this, and these two are the same. Well, no, not quite, but no, we're jumping the gun a bit. We need to go a bit further. If we look at C1 mz1, what's that in terms of z0? So looking back up here, that's going to be C1 lambda z0 plus C1 lambda z1 plus C1 z0. Okay? And why is that? That's because m minus lambda I z1 is equal to, by definition, z0. So mz1 is lambda times mz1 is equal to lambda z1 plus z0. So multiply through by c1 and we get that. Okay. Right, so what does that give us? Well, look, we had, so that thing is lambda z1, which is that thing, plus c1 z0, which is that thing. So now all we've left to show is, can this thing equal this thing? And we made a mistake here. That, of course, should be, bracket should be there when we differentiate, okay? But notice that m minus lambda I z0 equals, by definition, m minus lambda I squared z0. sorry, Z1, because you multiply by the definition of Z1. And since m minus lambda I all squared is 0, that's 0. So that means Z0 is an eigen vector of m. And so m Z0 is lambda times Z0, which is exactly what we wanted here. Lambda times Z0. Okay? Or put it another way, what you could do is say, well, C1 MZ1, we could just say C1 MZ1 as a lambda, C1 Z1 plus MZ0. MZ0 is lambda Z0. I've taken the lambda out already. And then I've one bit left. This one here, I've put that in there, and I've still got this one. And so they're both the same. Okay? So now let's go into a bit more detail of these critical points. So classification of critical points. So we're going to make some assumption. We're going to assume that the eigenvalues are non-zero. So in other words, that's called non-degenerate. So the if one of the eigenvalues is equal to 0, then you have to use the higher order terms. Because, for example, if just like a simple analogy, if we were to write, say it was just in one variable, and say we had dy by dt equals f of y, and then we had a steady state, and then we perturbed, then we'd get dy hat by dt equals by Taylor, well, write it out like this, and then by Taylor times y hat plus higher order terms. That's equal to 0. And then why do we ignore these? We ignore these, we're making the implicit assumption that this is not equal to 0. But if this is equal to 0, then you have to take the next order term, because you can't say that these are negligible compared to this, because these are order y hat squared, and if y hat is small, then certainly they're smaller than this. But if this is multiplied by 0, then it's incorrect to say you can ignore these. And so if one of the eigenvalues is 0 going into a system, it's sort of like the equivalent of that then you need to deal with higher order terms, and we're not going to do that. That's beyond the scope of this course. Okay? So now we're going to think, well, there's lots of different cases. So suppose lambda is real. Then the question is, are they both positive? Are they both negative? Is one positive? Is one negative? Are they equal to each other? And then if they're complex, do they have real part positive? Do they have real part negative? At least we know we don't have the case, are they equal to each other, because they can't if they're complex. So lots of different cases. So case 1, 0 less than lambda 1 less than lambda 2. And of course, they're obviously real if they satisfy an inequality. And so then going back to 2.6, we can write z of t is c1 z1 e lambda 1t plus c2 z2 e to lambda 2t. And we know that z1 and z2 have to be, they can't be parallel to each other. Oops, sorry, that was bad, putting those arrows there. Okay, so suppose I started off, and this is my steady state, P, or my critical point P. So suppose I made a perturbation to here. So in other words, I took C1 to be something, non-zero, and I took C2 to be 0. Then what's going to happen? I'm going to have the solution C1 Z1 e to the lambda 1t, and that's going to grow because lambda 1 is positive. So you put the arrow there. Likewise, if we go here, C1 is now negative and is going to go in this direction. Suppose I started off here. Then I've taken C1 to be 0. So I've just got C2, Z2, so I'll go there and go there. What happens if I start off here, where I've got a C1 and a C2? Well, I'll get a linear combination of the two of them, but because lambda 2 is bigger than lambda 1, as t goes to infinity, this one is going to dominate, which means that I'm going to go something like that. I'm going to be tending in the direction of Z2. And so if we take it goes like that, and then here it will go like that, and here go like that, and here go like that. And that's called an unstable node. Case 2, lambda 1 less than lambda 2 less than 0, again both real. And actually I'll do the eigenvectors in a different color. Z1, Z2, oops, not necessarily perpendicular to each other, Z2, and there's my steady state P, critical point P, similar sort of arguments, but with the arrows reversed. So if I start off here, I've got C2 equal to 0, so everything's Z1, but it's decreasing. Here, it'll go in that direction. Okay? Here and here. And now what happens if I start off here? Well, I've got Z1 and Z2, but as t goes to infinity, the e to the lambda 1t will go to 0 quicker, so again I'm tending towards Z2. But I'm decreasing So I'm going like that. So it's basically case 1, but with the arrows reversed, which is intuitively obvious. You're just changing. Another way you can think about this, you're simply changing the direction of time. And so this is called a stable node. So now what happens if they're equal to each other? Lambda 1 equals lambda 2, call it lambda. So this is what we had here. And then we had 2 subcases. We had this case here. So that we called case I. It's Z is equal to C e to the lambda t, where C can be anything. So there's my point P, and I start off here. Means I've given some C here. Well, let's now assume lambda is positive. Once again, they have to be real because they're, if they're equal to each other, they have to be real. And therefore, this is just going to grow off like this. Start off here, and just going to grow off in that direction. Here, go off in that direction, up in that direction. And that's called an unstable star. If lambda is less than 0, we have a stable star. What about case 2, where Z is equal to C1 Z1 plus C0 plus C1t Z0 e to the lambda t. Okay, so lambda bigger than 0. What's going to happen? So again, if we use different colors, call this Z1 and this one Z0. And this is P. So if I start off with C1 equal to 0, then it means I've just got C0 Z0 e to the lambda t, and then I go off in this direction. And if C1 was negative, I'd go in that direction. Now remember, in the previous ones, what we did was we did put one constant equal to 0, and then you're in one eigenvector, put the other constant equal to 0, and then we're in the other eigenvector. So now it's very tempting to think, oh, if I put C0 equal to 0, I'll get this one. Okay? But remember, you should be a bit nervous about this. Z1 isn't an eigenvector. So, because Z1 was something such that m minus lambda times Z1 was not equal to 0. And so you can see now, if I put C0 equal to 0, so that I get Z1 I automatically get Z0. So there's no way I can choose the initial conditions so that I don't get a Z0 and I do get a Z1, because I have to make that non-zero and that's there. Okay? So that's one difference between this and what we've done before. So suppose I start off here, then I've got a bit of Z1 and a bit of Z2. As t goes to infinity, they're both growing, but this is going to mean Z0 is going to win out, so this is going to veer towards Z0. So it's going to go off like that. What happens if I start here? Then what I've done is I've taken C1 bigger than 0. Okay, and when t is small, Z1 and Z2, they're sort of, maybe roughly speaking, equal to each other. If C0 was similar sort of value to C1, I'm going to have something that maybe starts off going like this. But eventually, this t means this one's going to win out. And so we're going to end up going up like that. What happens if I start here? Well, I might, or maybe if I start here, then I've got C1 and C0. If I start here, t is small, so they're both sort of comparable size, so I'll go like this. But eventually, this will win out. So what do? Don't do this because it's wrong. Do I go up like this? Well, no, because C1 is negative. So that's negative. So I come down like that. And that's called, and in fact that should be coming down, going like that, going like this towards this one. Okay? So that's called an inflected node. What happens if lambda is less than 0? Then again, we're going to have that one, if we take C1 to be 0. And now what's going to happen, if we start here, what's going to happen, so we've got, as t goes to infinity, we're going to go to 0, but again, this one is going to be the winner compared to this one because of that t. So if we were to start here, then we would end up going like that. Okay, because we're going to 0, we're going to the steady state, critical point, and we're going in the negative Z2 direction. And what happened if we would start here? Then we again have to go to here, and again we have to go along this direction.
Z2 and Z0 are the same.
Oh, sorry. Thank you, that should be Z0. Thanks for pointing that out. Yeah, sorry about that. I went back to the original notation. Thank you. So, well, if we're going to get back to there, going along this direction, there's two ways we can do it. One way is like this, and the other way is like this. So let's do this way first. Okay? And now the question is, could we go the other way? Could that happen? Let's look at t e to the lambda t for lambda negative. So initially this is going to grow, but then it's going to go to 0. Okay? So what that means is the Z0 component must increase initially and then decrease. But if I look at this projection here, what I'm finding is that, so I mean, if this would then go on out to here. This one would be done going out to here. What's happening here, if I start off here, this projection decreases first before it increases, which is not what this says. Whereas this one here decreases first of all, and then goes down like that. Okay? So it must be this one and not that one. So the projection onto Z0 increases initially, then decreases. Whereas here it would be decreasing initially before increasing. Okay? So now we have, so this is called an inflected node. And that one is stable. Yes, I should put down in the sort of obvious, that one's unstable. And that one's stable, inflected node, stable. What about next case, lambda 1 less than 0, lambda 2? Then usual thing. So now again, if we start off with, now we go back up to here. If we were to take C2 to be 0, so there's no Z2 to begin with, it's just Z1, then we have e to the minus something, because lambda 1 is negative, so we'll go like this. And if we start off here, we'll go like that. If we start off here, begin with no Z1, then we just have Z2, e to the lambda 2, t, lambda 2 bigger than 0, goes up like that, down like that. What happens if we started here? So if we start here, we've got quite a bit of Z1. So C1 is quite large, and we've only got a little bit of Z2. So C2 is quite small. So initially, it will look like Z1. But as t gets larger, then the Z1 component will become less, and the Z2 component will become greater. So it'll end up doing that. And then here, it'll end up doing that. Do that, and here it'll do that. So that's called a saddle point. And that's unstable. It does have a stable manifold, but as soon as you perturbed off this, it's just going to zoom off. So it's going to be unstable. So that leaves us with the final thing, which is complex eigenvalues. So lambda 1 is mu minus I nu. Lambda 2 is mu plus I nu, where mu and nu are real. Then what we should know is that the corresponding C1, Z1, C2, Z2 are a conjugate pair. So we need that in order to get real solution. Right, so again, that's from linear algebra. You should know that. So let's set C1 to be RE to the I theta. And let's set Z1 to be 1 KE to the I theta. Now, why is there a 1 there? Why could I not do 0 here? Why have I made the implicit assumption that that's non-zero? So I can normalize it. Okay, if it's non-zero, I normalize it and just call it 1, and then that's whatever factor it is. But if that was 0, well, suppose it was 0. Instead was 0 times something, which has to be non-zero here. So I don't know what will we call it. Call it gamma or something. Okay. Then look at MZ1. That'll be A, B, C, D times 0 gamma. And that would have to equal lambda 1 times 0 gamma. So for gamma to be non-zero equals 0, B has to be 0. Okay? If b is 0, the eigenvalues are real, not imaginary. Because if b is 0, here's the eigenvalues, a and d, and they're real. But we've just said we're looking at complex eigenvalues. So we can't have that. Okay? This leads to another thing, is that a few years ago in a different course I set a question where you had to work out eigenvalues of a matrix, 2 by 2 matrix. This one was easy to, this derivative was easy to work out. So that one there was easy to do. This one was extremely complicated to work out. This was easy to work out, and this was obviously 0. And what most candidates did was spend a huge amount of time working this out, and then multiplied it by 0. And then complained that the question sheet was too long. Because I just assumed naively that since it's trivial to see that this is 0, you automatically know the eigenvectors, the eigenvalues are the diagonal terms. Okay? So always be looking for those sneaky ways to save yourself time. Okay? That's just by the wayside. Okay? So Z1 then has to look something like this. And that's assuming, sorry, that I missed out a bit, that let's assume that C1 is RE to the I theta. And so this one here should be phi. So C1 Z1 is RE to the I theta, KE to the I phi plus theta times R. And therefore, what's Z? Well, Z is going to be, remember, it's going to be C1 Z1 e to the lambda 1 t plus C2 Z2 e to the lambda 2t. So this we can write as e to the mu t times C1 Z1 e to the minus, well, it doesn't really matter, see the way I've defined the lambda 1 with a minus, so these are complex conjugates. So this is just 2 times the real part of that. Okay? So what we'll do next time is we'll actually go through that and write down, so the solutions will just be cosines. And then what you see is if the solutions are cosines, then they're oscillating. But we'll go through that next time. And so if mu is positive, you've got an oscillating solution that's amplitude is increasing in time, so it spirals out. If mu is equal, it's oscillating like that, which means just a closed curve, and if mu is negative, it's going to 0. But we'll go through that in more detail the next time.